All right, we'll go ahead and get started. So today we are fortunate to have Professor Caroline Morley from the University of Texas at Austin. Caroline got her undergraduate degree at MIT and then traded the overcast skies of Boston for UC Santa Cruz, where she got her PhD before going back to the cloudy skies of Boston as a Sagan Fellow at Harvard, before going back to somewhere else where it was more sunny at UT Austin as an assistant professor in 2018. So Caroline's an expert in brown dwarf and exoplanetary atmospheres, also does a fair amount of observing, and for all of that work was awarded the AAS Annie Jump Cannon Prize several years ago, and is a Sloan Fellow. I mean, many things that I could take the rest of our time just talking about. So today, Caroline's going to tell us about new observations of Earth solar system analogs. And without further ado, thanks, Caroline.
Great. Thanks for the introduction. It's great to be back here in Boulder. I always enjoy visiting Boulder, and I don't usually get to visit the same department 2 years in a row, so this is very exciting for me. I made a fresh talk for you, so don't worry. It's not like a sequel if you weren't here last year. So let's jump in. So I'm going to jump in the same way that I do when I start teaching undergraduates of any level, and sometimes even my graduate students, which is to say that I think that we live in a very special time in the history of humanity. We are, of course, not the first people to look up at the sky and wonder if we are alone, but I think we, as a generation of scientists, are probably going to be the first ones to really start answering that question with science. And that's all happening within my field of exoplanet atmospheres. So what's led us to this? So, of course, a lot of what's led us to this is technology, right? That we started with telescopes, that we just pointed at the planets in our own solar system. We built telescopes capable of discovering exoplanets outside of the solar system. We further used telescopes, including current new telescopes, to then characterize exoplanets for the first time. And our future includes bigger telescopes on the ground and specially designed telescopes from space that'll be custom designed to be able to start answering this question of, is there other life around us in the universe? An exciting time. So when my students, my undergraduates, started in elementary school around the same time that I got into the field, the kind of landscape of the number of planets that were known looked like this. There were just a few hundred planets. Most of them were discovered by the radial velocity method, just a few transiting planets that cross in front of their star. By the time my students were starting high school, we knew of thousands of planets. And this was driven by the revolution of the Kepler Space Telescope, which was custom designed to discover planets, right? A planet discovery machine. This has only continued in the last few years, and now we are at a count as of the last week of January of 5,572 confirmed exoplanets. So we often take these planets and put them on a plot that looks like this. So this is going to show the period of the exoplanet's orbit and the mass of the planet. Let's throw up our solar system planets on there to start. And so one of the things that I think about a lot is what would have happened, the alternate universe we would have lived in, that I would have done my work in, if the exoplanets actually looked like this, the population of exoplanets, if they all looked like our solar system, rather than what we've actually discovered to date, which looks like this, right? We've filled in this diagram. We find big planets on close orbits, big planets on distant orbits. We find planets all the way from bigger than Jupiter in mass down to Earth size in mass. We really cover this whole space. And so, you know, in the alternate history, right, I think about this. It would have taken us decades just to find the first giant planets. With Kepler, a mission custom designed to be able to find Earth-like planets, we would have found just a few planetary systems. It would have looked totally different. But now we're at a stage where we have these planets, and these planets are often quite easy compared to solar system planets to characterize. So we've really gone into this era of detailed planet characterization, largely driven at the moment by JWST, which I'm showing here. Okay, so let's go back to this plot. So one of the things that I really like about modeling exoplanet atmospheres is I'm not beholden to any particular part of this diagram. I can model planets all over the diagram. And so there's a lot of stories I could have told you today that I'm not going to tell you. So one of those is about these sub-Neptunes, these mysterious planets between Earth and Neptune in size. We have no analogs in our solar system. And our data to date suggests that these are obscured in these hazes. But I'm not going to tell you about that. And I could have told you, and I actually did tell you about this last time, so if you have a really good memory, about some of the observational work that I've led out of UT Austin, where we look at the edge of this diagram where planets are rapidly losing their atmospheres. And we can observe the kind of helium exospheres around them. I'm not going to tell you any more about that either. The story that I'm going to tell you today is about our path towards observing things, characterizing planets that are more like our solar system planets. So a path towards our true Jupiter analogs, which will pass us through their free-floating counterparts, so without a host star, and also their youthful progenitors. And then I'll also tell you about our rocky road to terrestrial planet characterization. So let's start with the giant planets. So something we might want to know is how and where do giant planets form? And there's 3 ways we might start probing this that I'm going to tell you about right now, that we can probe using measurements of their atmospheres. So way 1, so in our solar system, if you look at the enhancement in carbon in the atmospheres and the giant planets in our solar system, we see that all of them are enhanced compared to the sun in carbon, Jupiter by a factor of 3, Uranus and Neptune by about a factor of 100. We interpret this as being enrichment in metals, right, from accretion of solids relative to accretion of gas from that protoplanetary disk. So we're accreting solids into the atmosphere and enhancing it. We might want to map that out for exoplanets as well to understand how they accrete solids and gas. We also might want to go into more details, right, and look at the different elements, not just carbon, right, like we can do in our solar system. Let's look at other species that are hard to detect in the solar system, but possible to detect in exoplanets. And so the most famous example of this is the carbon to oxygen ratio, famous because these are 2 of the most abundant elements, right, in the galaxy, and because they vary the most at different distances from the host star because they condense. We have our ice lines for water, CO2, and CO at different distances. So by combining these, right, how much solids you accreted from looking at the metallicity, with that ratio of those elements, you can start to figure out the location that you accreted much of your material from. If you know anything about disks, you're probably looking at that and being like, that's too simple. That's true. Okay, and we can also start to use other tracers of planet formation. So one of these that's been historically used in the solar system, pretty famously for lots of different planets, is the deuterium to hydrogen ratio. And so in our solar system, this traces various things. But if you look at the ice giants, Uranus and Neptune, you see they're enhanced in deuterium. That's because they've accreted ices, which because of chemistry in the disk, end up enhanced in deuterium. And so if we can start to do this for exoplanets as well, we can start to understand how those planets accreted their ices. We're looking at objects that might actually be massive enough to fuse deuterium. And because these objects are fully convective, once you start fusing, you lose the deuterium from your atmosphere. So we may also be able to use measurements of this to trace deuterium fusion. Okay, so our isotopes can capture these kinds of details. We'll come back to these ideas when we start looking at data a little bit later on in this talk. Okay, when we look at giant planets, we may want to also know more details about the physics of their atmospheres. So I'm going to play you a movie now. This is a flyover from Juno of Jupiter. This is the kind of thing that keeps me up at night as somebody who tries to study planets from much more limited data than we're able to get here. But nonetheless, from our exoplanets, we might want to know things like, what is the weather and circulation like on these planets? Which planets have storms? Which planets are variable? Are the atmospheres stratified? Are they kind of layered? Or are they mixing deep layers kind of continuously from underneath? And are there processes that we see happening in our own solar system present on some of these exoplanets as well? Things like these ion-atmosphere interactions that can give us planetary aurorae. So we might want to know the answers to lots of different questions like this about the physics of atmospheres. Okay, but let's go back to the basics. So we can model planets, and this is kind of the bread and butter modeling in my group. So this is showing different model atmospheres here as the solid lines here, from the hottest atmospheres on the right to the coolest atmospheres on the left. We calculate these atmospheres in radiative convective equilibrium. They're convective in the deep atmosphere, then they're radiative once photons can transport that energy. And so we calculate this in a way that we call self-consistent. We mean that it's consistent with the chemistry. And the chemistry changes dramatically over this temperature range. So the dashed dot lines here are showing you some of that chemistry. Is this a laser pointer? Maybe. Yes, laser pointer. Okay, so to the right of this line here, most of our carbon is in the form of CO. To the left, it's in methane. Same for this line here. We have nitrogen on the right and ammonia once it gets cool enough. So we expect to see some major transitions in the spectra of our objects, right? From having CO features at warm temperatures to lots of methane features at cool temperatures. Okay, so that's one of the things we expect to see. The other thing these models let us do that ends up being super important is that they connect the deep adiabat, right? So these are objects that are convective all the way down. This is giving us the internal entropy of our object. It lets us connect that to the cooling rate. So as our objects cool, they have to cool through that planetary atmosphere. The atmosphere sets the cooling rate that they're able to do that at. And so we need these kinds of atmosphere models to serve as the boundary conditions if we want to understand how planets evolve over time, how they thermally evolve, cool, and shrink over time. And so we can do that. We did that here. So this is from a new paper that I put on arXiv a couple weeks ago. So this is showing for those evolution models controlled by those atmospheric boundary conditions, how planets of different masses, so the numbers labeling each line are giving you different masses in Jupiter masses, how they cool off over time. So you can see that they all start hot and cool down over time. They pass through this sequence, right, from the hottest ones are M dwarfs, through L dwarfs, T dwarfs, and the coolest objects, the Y dwarfs. And so we use these evolution models pretty directly to take our observations, which often give us something like the luminosity, the temperature of the object, and connect, and we might know the age of the star that our planet is around, for example. And it lets us actually get a model-dependent mass by reading kind of which line we're crossing here. So every time you see a mass measurement of one of these planets that's been measured as a young planet that's been directly imaged, almost all of those just directly rely on calculations like this to give you the planetary mass. You can look here and see that there's some useful features here, that a young, less massive object will have the same temperature and therefore about the same chemistry in its atmosphere, about the same spectrum, about the same spectral type as an older, more massive object. So there's a whole game of observing these older objects and using them as proxies for these kind of planetary mass objects. Okay, but we've missed something big in these calculations, which is the fact that you condense different species in these planetary atmospheres. So clouds is a subject that I've worked a lot on over the course of my career, from my very first papers to my most recent papers. So this is showing us where different clouds form in these atmospheres. So for example, if we look at this water line here, to the right of this, it's hot enough that water's in the vapor phase. To the left is cool enough that water can condense. So we form a cloud where a given pressure temperature profile meets that condensation curve. The most important clouds here are the most massive ones. The most massive clouds are set by cosmic abundances. Those end up being the silicate clouds at these high temperatures. And then eventually at cool temperatures, we start condensing these massive volatile clouds out like water and ammonia. And so when these form, they're actually really important for altering the evolution of our substellar objects. So this is the same plot that I showed you before, now with a snake in the corner. I'll get to that in a sec. And so these ignore the effect of cloud opacity. Now I'll add the dashed lines that are going to show you the same model masses, but now with clouds. And so you see here, we have these changes by something like a couple hundred Kelvin at the kind of most significant regions of this through here. And so we need to understand clouds to be able to properly understand the evolution. What's happening right here is that the clouds dramatically clear at the L to T transition. So the L dwarfs, which are hotter than 1300 Kelvin, are cloudy. The T dwarfs are relatively clear. We know that empirically from observations. We can also see this in the actual population of objects that you see. So prediction from evolution models like these is that you would pile up objects at about 1300 kelvins in mass, in temperature, where this cooling kind of levels off. And if you look at the most recent data that counts everything in our solar neighborhood, we see exactly that. It's a pretty sweet confirmation of this model prediction that we have this bump at 1300 Kelvin. So this is for kind of solar metallicity field objects. So that had been done before. What my models do for the first time is evolving these at lower metallicities and also at higher metallicities. That's really important because if you remember, the metal enhancement of Jupiter is about 3 times solar metallicity, lining up with this plus 0.5. So we have that metallicity now, including clouds for the evolution for the very first time. So this is being used right away to understand our observations of these young, warm Jupiters. The next step is something that my student is valiantly working on right now. The water clouds are tricky for lots of technical reasons. They've never been included in a wide grid of models. They've never been included in the evolution before. We expect them to have kind of a similar bump to the evolution. And so he's working on doing this for his thesis project right now. OK, so let's think about our path towards these true Jupiter analogs. So our true Jupiter analogs are going to be around old stars, right, in our kind of local neighborhood. And they're going to be, around the mass of Jupiter, or maybe a little bit more massive. And so if we look at where those form on a plot like this, we see that they're going to be down here. I'll put my triangle up here in this corner. So if we look at things between 1 and 10 gigayears old and less massive than about 13 Jupiter masses, they're all going to be down here in this coldest spectral class, the same as these wide dwarfs. So when we look out into the field and see wide dwarfs, we're going to see everything that ranges from these higher mass objects over here to these lower mass objects over here that all have about the same temperatures. OK, so let's talk about the wide dwarfs. So we've discovered a few dozen of these objects that are right in this temperature range, between about 250 and 450 or 500 Kelvin. We discovered these mostly with the WISE survey, which looked in the mid-infrared. You find these in, if you think about it in like the way people talk about extragalactic surveys, these are W1 dropouts. So these have a big absorption feature. It's from methane at 3.6 microns that's causing them to be almost invisible at these wavelengths, but bright at 4.5 wavelengths. We can plot this as a color magnitude diagram. So this color here on the x-axis versus this magnitude. And we've observed a bunch of these, and the starred ones here are ones that are included in the first big wide dwarf survey with the James Webb Space Telescope. If we think about what masses these objects are likely to have, it's going to differ by the temperature of the objects we're looking at. So for the coolest object down here at about 250 Kelvin, it has to have a planetary mass under 13 Jupiter masses. As we go to these warmer objects, more and more of them are going to be kind of over 13 Jupiter masses older objects. I'm going to show you the spectra of 2 of these objects that we've observed with the James Webb Space Telescope, but you haven't earned it yet. I'm going to show you the ground-based data that we worked very hard for that served as kind of our precursor science for this JWST data. So let's look at that. So this is led by Brittany Miles when she was still a graduate student at UC Santa Cruz, and me and Andy Skemmer. These are observations taken with the Gemini telescope in the mid-infrared in M-band. These are very challenging observations to take from the ground. And so I remember when Brittany first showed me these spectra, And she, oh, this is the wrong spectrum. Let's look at this one. Okay, when Brittany first showed me this spectra of these objects here, so the observation is shown in this purple line here, and the gray points are showing the best fit model from the original grid of models that I gave Brittany. And so she showed me the data. She was still a grad student, right? She's like, Caroline, I worked really hard on this. Like, I'm pretty sure it's right, but it really doesn't look like the model that you sent me. And I was like, oh, yeah. Indeed, it does not. And so there's this, if you look closely at this, there's kind of this feature here, like a big W shape. That's from carbon monoxide. So if we include extra carbon monoxide in our model, it looks like this. So why wasn't the carbon monoxide there in our model in the first place? Well, it turns out that this is being mixed from deeper, hotter layers in the atmosphere. So if you remember this plot I showed you before, where there was a lot of CO, right, at these hotter parts of the atmosphere and more methane up here, if we mix these CO layers from deep here up the temperature profile, we're able to kind of reproduce the amount of CO that we see in this actual object. So what this means when we look at this for our whole survey is that with this data, this valiantly won data, we're able to connect these observations and the inferred CO abundances to the mixing rates in our atmospheres. And it actually matches a prediction from the models where the coldest objects will be fully convective, the slightly warmer objects will be a little bit less vigorously mixed because they have these stratified radiative zones in the middle of their atmospheres. So that was really exciting to us and kind of drove a lot of the ways we were thinking about doing science with the James Webb Space Telescope. Okay, so you've earned your JWST data now, and it's beautiful. So the first object we're going to focus on is this object, WISE 1935. So this is an object that's in this kind of bin that we thought was something around 400 Kelvin. So we're going to look at our data of this. This is near-spec data taken from about 3 to 5 microns. And we're going to compare this object just empirically to another object in our sample that has the same apparent or absolute magnitude that we see here. OK, so here's our comparison. So our object of interest is the black line here. The object we're comparing it to is this green line. You see all kinds of beautiful features in here. All of these are features, not noise. It's water through here. It's that big CO feature through here. We see a little bit of CO2. And we see this broad methane feature through here. This is from a methane feature at 3.3 microns. Let's zoom in to the most interesting part of the spectrum, which is this little tiny bump right here. There it is. So we see this bump here. This bump is right in the middle of the Q branch of methane, the strongest part of our methane absorption. We've never seen this before in any brown dwarf that we looked at before. And so what we think is going on here is that to get this feature in emission, right, instead of in absorption, we have a temperature inversion in the upper atmosphere of this totally isolated object with no star to be driving a temperature inversion like we get in our solar system. And so here's our retrieved pressure temperature profiles. So this is the retrieved one for this object with the inversion. And you see it's hotter by a couple hundred Kelvin, right around like 10 to the minus 2 bars. And so there's nothing to drive this really in the system, except for we know that you can drive temperature inversions and methane emission in solar system planets if you have auroral activity on those planets. So our picture here is that perhaps we are seeing the effects of having high magnetic activity on this object. Some source of electrons, maybe something like an extrasolar IO that's depositing electrons and generating energy deeper into the atmosphere that lets us have this temperature inversion. OK, there's a lot of question marks and caveats with this, but I think it's super exciting. I also wanted to point out here, and I'll do this a couple more times during the talk, there's lots of expertise here at CU that I think would be really helpful for continuing to work on this. Me and Sebastian and his student are already thinking about doing these kinds of models. I think there's lots of other people here too who know something about space physics. So, okay. Continuing on to my favorite object in the whole galaxy, WISE 0855. So this object is 250 Kelvin. It is 2 parsecs away from us. It's the 4th closest stellar system to us. Because we know it's about 250 Kelvin, and we know that it is younger than the age of the universe, we can calculate that from our evolution models, right, that its mass should be something like 3 to 10 Jupiter masses. So squarely in the free-floating planet regime. And so the question is, how do you get objects like this, right? How do you get these free-floating planets? Did it form like a star, kind of the tail end of the star formation process? Did it form like a planet and then get ejected out from its planetary system by something even more massive? So let's look at its atmosphere to try and figure that out. So we have 2 data sets for WISE 0855. The first was taken as part of a guaranteed time observations program with JWST. Looks like this. So it's a near-spec G395M spectrum from 2.5 to about 5.5 microns, resolution of about 1,000. We have another set of data from a program that Andy Skemmer led along with Brittany and me. Again, using the same mode, this G395M, same wavelength range, but instead of just looking at it for like a snapshot of time, we looked at it for 11 hours. The idea here was actually to be able to see heterogeneities on the surface, right? And as it rotates around in about 11 hours, we'll see variability. What we're hoping to see is that that looks like water ice clouds are kind of heterogeneous on the surface. And so we see that water ice feature around 3 microns cause variability at those wavelengths. We got this data in like the middle of December. We're still working on it. By we, I mean Brittany is still working on it. But I'll show you this is a plot of the percent change as a function of wavelength going through our time series from the top to the bottom here. So a few punchlines that we know already. It is variable. Phew. We really don't want to look at something to try and detect variability and have it not be variable, so that's good. And it does not look like the water ice models that I ran for the proposal. It looks like we're seeing kind of chemistry variability. We're seeing banded structure through here that looks a lot like the CO features. So we're puzzled by this. We're working on it. I don't have answers for you yet, but there's something else I want to show you. So something that I predicted back in 2019 is that we would be able to see deuterium for the first time in these cold objects using this feature from deuterated methane, CH3D. It has a strong feature around 4.55 microns, which is kind of right in the middle of the observing windows we're looking at here. So this is the prediction we made, kind of taking deuterium out and then back into the model. So the very first thing that we did when we got our data in hand, so this is actually using the guaranteed time observations data. My student Melanie ran an atmospheric retrieval, so taking the data, varying all of the different components in the atmosphere to see what was there. And we think we see it. So I'll show you the spectrum first, then I'll show you our posteriors from our retrieval. So the feature is in here and here and here. We also think we see phosphine, which is exciting for different reasons that I don't have time to tell you about. And so it's kind of falling right in there. So you need a high signal to noise spectrum to see it. Here is our posteriors. So here I'm showing you the 3 things we talked about at the beginning of the talk, right? Metallicity, C to O ratio, and this deuterium to hydrogen ratio. So what do our results mean? So we retrieve a slightly subsolar metallicity. This is broadly consistent with what we see in the solar neighborhood in stars. We see a slightly subsolar C to O ratio. The sun is like 0.45 or so. This is consistent, again, with the ranges that we see in the solar neighborhood. And we see a protosolar D to H ratio. Protosolar is something like 2 times 10 to the minus 5. And so putting this all together, this is how I'm wording it right now, okay? No evidence that it didn't form like a star. I think that's accurate. Okay, so that's really interesting. This is one of the first times we've been able to do this. And this really opens the door to using this D to H ratio outside the solar system, which is this like classic tracer of planet formation and atmosphere loss in our own solar system. And so for the very first time, we're able to put this point on here. And I think we'll see more points on here in the near future, some of them mapping out this deuterium fusion, right, putting constraints on objects that are more massive, and hopefully some of it pushing towards these planetary mass objects. Okay, on our path to true Jupiter analogs, I wanted to show you what I think has a good case for being one of our first pictures of one. So, JWST is so sensitive that for the very nearest stars, we're able to detect kind of true old Jupiter analogs. This is possible only for the nearest by stars because JWST is really not designed for very high contrast at very small separations on the sky. You need them to be close to us so they get further apart on the sky. And so the star that we're looking at is Epsilon Indi, which has been known to have a planet. Well, it's really been known to have a planet for a long time. If you look at this stars and planets, planetary systems in fiction, all the way back to 1966, science fiction writers were putting planets around Epsilon Indi. It's one of the most famous stars in the sky. And these really, you know, this takes us all the way to like Halo, the harvest planet, is around Epsilon Indi. So remember that. Okay, good. So we look around Epsilon Indi. We have radial velocity measurements and astrometry measurements that tell us that there's a planet in the system. We can predict where it will be. We get JWST time to observe it, led by Elizabeth Matthews. And here's what we find. So this is our picture. This is where we predicted Epsilon Indi would be at 10.65 microns. This definitely looks like a planet. So we think we detected a different planet in the system than our kind of dynamical information was telling us about. We've run this through all the you know, things you might think of, like, is this actually like a high redshift AGN? The answer is no. There's no way a high redshift AGN is like this bright with this color and stuff. So we think, we're convinced, we've convinced ourselves that this is right. This has a temperature of about 320 Kelvin, so right in this realm of these cold brown dwarfs I've been talking about. That gives it a mass of something like 10 to 12 Jupiter masses for Epsilon Indi's age. So if you're comfortable with a true Jupiter analog being 10 Jupiter masses, I think this is a beautiful picture of our first Jupiter analog. And I wanted to point out here that we'll be detecting more of these kind of older, colder giant planets, both with JWST. I think there's a few more systems we'll be able to do this really well for. And also in the near future with surveys from the ground, right? We're starting to get ground-based technology that can look at these systems, and we're starting to get a lot more dynamical information. So with the full Gaia data release, we'll have hundreds of potential planets that we could detect from ground-based telescopes, like current 10-meter telescopes or 30-meter class telescopes. Okay. So the future is bright, I think, for looking at these coldest Jupiter analog kinds of worlds. JWST is really giving us nice data for objects that are nearing solar system giant planet temperatures. With this, we can start to learn all kinds of things about their atmospheres, their compositions, right? The dynamics from that mixing of the chemistry, clouds, even things like deuterium abundances that seemed like a stretch to people before we were actually doing it. And this is paving the way for directly imaging solar system age planetary systems. And I crossed out in the near future and said now, because I think the EPS Indi detection has it. Okay, so for the next part of my talk, we're going to switch gears from looking at our Jupiter analogs to looking at our path towards rocky planet characterization. So of course, in our solar system, our terrestrial planets, right, started with roughly the same building blocks of volatiles to build their atmospheres, but ended up with 3 planets that have atmospheres that look very different from each other, right? We have Venus, which we think lost all of its water inventory, right? Evaporated its oceans, lost its water from the upper atmosphere, was left with this CO2 thick atmosphere. Earth, with its beautiful oceans that help it sequester its CO2 deep in the planetary interior. And then Mars, which we think used to have that thicker atmosphere, water on its surface and has since been shaped by the erosion of that atmosphere. But of course, when we look at exoplanets, I think the thing that keeps me up at night is that they're actually all going to look like a different planet in our solar system, which is Mercury, right? Which doesn't have an atmosphere at all. And so let's look at that and why we might think that we might see extrasolar Mercuries maybe as often or more often than we see the other planets. So one of the reasons is that we are not looking at planets that are around sun-like stars when we look at them with our current technology, with JWST. The reason for this is because of the size of the stars relative to the planets. So this is showing the sun relative to Jupiter, roughly to scale, which gives you about a 1% transit depth when the planet passes in front. This is one of the smallest possible stars, right? Just barely hanging on to the main sequence, TRAPPIST-1, with an Earth-sized planet and going in front of it, also gives you about a 1% transit depth. Once you do the math, you pretty quickly figure out that the only temperate terrestrial planets that will have potentially observable atmospheres with JWST will be planets that orbit stars that look a lot more like this TRAPPIST-1 planet than they do like the sun. If those planets have atmospheres, we'll be able to potentially detect them. So it looks like this. I've put little warnings when I show you simulated data now that we have real data from JWST as well. This is simulated. So this is for TRAPPIST-1b. So the TRAPPIST-1, this little star, has these 7 planets that were discovered around it. I ran models for all of them, but I'm showing you the TRAPPIST-1b ones here. This is in transit when the planet passes in front. The starlight goes through the planet's atmosphere. You get this bump from CO2 in our simulated observation. And this on the bottom is the emission spectrum. That's from when the planet goes behind the star. You lose the light from the planet itself. And here again, we get this CO2 feature in our simulated data. Basically, if these planets have atmospheres, we'll be able to see that they're there with JWST, and we'll be able to see the major greenhouse gas that's there, whether that's water, like in the Earth simulations, CO2, like in the Venus-like simulations, or methane, like in these Titan simulations. Why do we think it might not be there? So there's 2 potential problems. So the first one is that these smallest stars, if you look at how long it takes them to hit this main sequence, right, of constant luminosity here as a function of age, while the sun hits it really quickly within, just a few million years, these late M dwarfs take 1 to 2 billion years to actually hit that main sequence. And so what that means is the planets around them are going to have a much brighter star. So even if they're in the habitable zone now, right, they weren't for much of their lifetime. The second potential problem is that we know from observing M dwarfs, and many people here work on this topic, we know that especially the young M dwarfs have really high UV fluxes. They probably have really energetic stellar winds, really relative to sun-like stars. And we think that these might erode the planetary atmospheres on much faster timescales than happens in our solar system. But we need to model this, right? Because astronomers look at it and they're like, no way, you're not gonna have atmospheres, they're not gonna survive. It's too just bad an environment for a planet to live in. But you talk to the planetary scientists and they're like, I'm not worried. You're like, why aren't you worried? They're like, because planets outgas material for up to billions of years as well. So I was like, okay, we need to model this together, right? We need to model the outgassing rates as a function of time for a whole variety of different possible planets. And we need to couple that to understanding the atmosphere loss. So that's what my student, Katie, did for her master's project. She ran coupled mantle evolution and atmosphere loss models to understand the evolution of these terrestrial planets around M dwarfs. So she took a mantle evolution model developed first by Brad Foley, and she turned off all of the oceans, all of the carbon silicate cycle, all of the volatile recycling, turned all of those off because what we're simulating here is objects interior to the habitable zone where you might have water on the surface that let you do all of these more complicated things. And so we're left with something that just kind of cools the mantle over time and continues to volcanically outgas. She coupled that to parameterized results from these detailed MHD models of the stellar wind stripping of CO2 from these stars. And she used 2 different values because it turns out that this ends up being the most uncertain part of the problem, is how fast this happens. Okay, I'll show you Katie's results in a minute, but I'm going to show you the observations first. So some of the very first hints we were getting about atmosphere loss on these planets came from Spitzer observations. So I'll introduce you to LHS 3844b. This is a super Earth-sized planet on a half-day orbit around one of these small stars. It was one of the first terrestrial planets discovered by the TESS mission, discovered early enough that we could apply for Spitzer time before Spitzer turned off. Can't do this for anymore. So the idea here is to observe the whole phase curve, right? Because remember, the orbital period here is only half a day. So that's actually tractable. So you observe the whole phase curve. You see how hot the day side is relative to the night side. You have a thick atmosphere. It takes energy from the day side to the night side. So they have roughly the same temperature. If you have a thin atmosphere, you end up with a hot day side and a cold night side. So let's see what we actually get. OK, looks like this. So that's our secondary eclipse. We see this deep secondary eclipse. This is where transit happens. So we see this large amplitude phase curve here, this deep secondary eclipse. So this is consistent with our no atmosphere picture, right? This high day to night temperature contrast means that for the first planet we looked at, right, something more irradiated than anything in our solar system, about 800 Kelvin, we found no atmosphere. Okay, enter JWST. This is now our workhorse for doing these kinds of measurements. So one of the first systems that people started looking at was the TRAPPIST-1 system. This is very favorable because the star is so small and because there's a bunch of planets in the system. So there's 2 programs I'll tell you about today. One of them looked at the innermost planet, TRAPPIST-1b. This was led by Tom Green. And the other one was our program led by Laura Kreidberg of TRAPPIST-1c. TRAPPIST-1c has the closest, of any of the TRAPPIST planets, has the closest kind of irradiation levels to Venus. So it's our Venus analog in the TRAPPIST system. The plan for both sets of observations was very similar. Observe eclipses, right? Observe them at the wavelength where CO2 absorbs most strongly. And so if the planet has a bare rock with no CO2, we'll be able to easily detect a deep eclipse there that we're able to see. The planet is bright. If instead the planet has lots of CO2 in the atmosphere, it's going to make it look a lot darker at those wavelengths because we have this deep absorption feature here. That's going to make the eclipse very hard to see. So that's kind of what we're hoping for, right? If we're hoping to detect a Venus analog, is that we get this kind of really shallow, hard to see eclipse. Okay, let's look at the TRAPPIST-1b data first. So the TRAPPIST-1b data, you see this beautiful eclipse in here. You can plot the point here. So this is the data point that they measure. Totally consistent with like a dark, solid, rocky surface. This is a simulated data point there. Okay, so that's TRAPPIST-1b, basically ruling out any atmospheres you can put together that have CO2. Now let's look at TRAPPIST-1c. This is our observation. So again, we can see that deep eclipse in the data. When we plot it compared to our models, it looks like this. So still a pretty high point. We're ruling out these kind of most Venus-like models down here. It's consistent with either being a atmosphere-free planet or having something thin and CO2 poor on the planet. And so yes, we did propose for another cycle, another wavelength in cycle 3 to nail this down and really understand whether there could be an atmosphere that's poor in CO2 on this planet. But this also gave us an upper limit now for our models, right? Because now we know that TRAPPIST-1c has very little CO2. We can put a constraint on it and then try to match it with Katie's models. So my student Katie did this, again with her coupled models that I told you about a second ago. And these are the results from that. So this is showing time and the surface pressure of her pure CO2 atmospheres here, starting from 3 different initial carbon inventories, so 2.5 times the Earth's inventory, 0.25, and then 0.025, so something starting poor. To be able to match the current constraint, which is down here, this 0.1 bars is our constraint, then essentially we have to have less carbon to start than we do in our own solar system. So at the time that TRAPPIST-1c started this kind of stellar wind-driven escape mode, it had less carbon than either the Venus or Earth does today. So it either started dry, like formed dry, or it potentially lost its volatiles early, right, in some kind of hydrodynamic phase before the stellar wind-driven phase started. Okay, great. There's a ton of connections to work that's being done here that I wanted to point out. So results from Dave Brain's mock project that he's running could basically be like directly inserted into this. It's like the perfect set of models to put into this to be able to really understand the atmospheric escape for a broader range of planets. There's also a lot of mission work here that's giving us some critical observations in the future. So the MANTIS project, which Brianna Indahl and David Wilson are leading, is going to get us the EUV observations, which are sorely lacking right now to be able to go into those atmospheric escape models that's driven by EUV. And then Zach and Sebastian and I have an ongoing HST archival program to better understand this UV-driven escape as well. Okay, I'm going to show you one more JWST observation. This is for that same planet that we looked at earlier, LHS 3844b, that didn't have an atmosphere that we measured with Spitzer. We nonetheless pursued observations with JWST to look at its surface, because we wanted to see what does the spectrum of the surface looks like, what kind of rock is it, and we also wanted to see if there was anything that could be volcanically outgassing, like SO2 or something like that. We don't see any of that. And this is our spectrum of the surface, which is consistent with a basaltic surface. So we can compare to 3 different kinds of rocks here, basalt, ultramafic, and granitoid rocks, and we see that it's consistent. So this is the first spectrum of a rocky planet's surface, to my knowledge. This is the closest to geology that we're getting right now. Okay. And this is really just the beginning of this, right? That JWST, just in its first 2 cycles, is observing 25 planets smaller than 1.8 Earth radii. I've shown you the data of 3 of these, 3 of the emission spectra. Oh, another CU connection. I also got to see that planet today. Pat, graduate student, showed me. And on top of these, which were proposed for, there's 500 hours of observations going into exactly the kinds of observations I showed you with the TRAPPIST planets, where we observe at 15 microns. So that's what they chose to do with the director's discretionary time. So this is broadly relevant to our understanding of these small planet atmospheres. Okay, I wanted to end my talk by talking a little bit about what happens next. So we finally have a lot of the tools that we need to do really interesting science with exoplanet atmospheres, right? To answer some of the questions we have and start to ask new ones. And so I'm involved in a bunch of JWST programs, so I get like lots of emails every month in my inbox. It's like, Caroline, what does my data mean? That's going to continue in the coming 5 years, right? It's a growing avalanche of data on exoplanet atmospheres, giving us a lot of room to explore, explain what's going on. So there's lots of different aspects of that I'm thinking about, and my group's thinking about that. Things like clouds, compositions, dynamics, other physics like aurorae, atmosphere loss from planets large and small, and also starting to think a lot more about computational advancement, because the volume of data is going up a lot. And so I think we need some more computational advancements to really understand that. Okay, the first pie chart I'm showing you here, I have 2 pie charts for you. First pie chart, this is JWST's cycle 3 hours requested. Exoplanets almost beat extragalactic for the first time in hours requested, so I think we should try to continue that trajectory in the future and beat them next time. This is the largest fraction of time that's ever been asked for exoplanet science on any of our major facilities. Okay, I'm going to show you one more pie chart, which is what my group's planning on working on in the next 5 years in terms of like the breakdown of work. Because sometimes I give talks and people are like, you're an observer. I'm like, I'm actually not an observer. I actually just work closely with observers. So something like 40% of the work in my group is on that self-consistent modeling, taking physics and chemistry, running models, see what we expect to see. About 30% on this retrieval modeling. We have a big new $1.5 million grant to put some of these computational advancements into the retrieval modeling. So that's going to be a growing part of my group as well. About 15% on other modeling efforts. So like the atmospheric escape stuff kind of falls into that, like things that are new to me and interesting. And then about 15% on leading observations as it is interesting to me. Okay. Why here, right? Why come to CU Boulder to do this? So the next 5 years of science, I think we'll see much tighter connections between astronomy and planetary science. And CU Boulder is a really rare example of a department that has both. So there's two reasons for that. Reason one is that as we're starting to get this really beautiful data of exoplanets, I think it's more similar to what solar system remote sensing people are used to seeing. And so we can get them to think about data that looks like this much more readily than we were able to with lower signal to noise, lower resolution data. And the second reason is maybe more fundamental, which is the planets we're observing are more similar to the solar system planets. The intuition that people have built from decades of studying the solar system applies more readily to the planets that are closer to the solar system properties, right? And that's true for both giant planets and terrestrial planets. Then some of the hot gas giants, right? Once you get to be like a 3,000 Kelvin planet, it's hard to bring that Jupiter intuition into it. And so I think this department really benefits from continuing to have people who can talk to both planetary scientists and astronomers with a focus on kind of the interdisciplinary work like I've shown you today, rather than just having like lots of multidisciplinary efforts. Okay, I wanted to put up some specifics as well about the kind of complementary expertise I have to the exoplanet group here. So I have kind of ongoing collaborations with Zach Berta-Thompson already. He does the observational side. I interpret his data for HST and JWST. So I could very easily imagine kind of jointly advising students who are interested in both theory and observations. I think there's really natural connections to the UV work that's being led largely out of LASP with the mission work there, kind of characterizing the current and past environments of planets. I could imagine contributing to some of these missions, right? Your science traceability matrices. I'm the science part of that, hopefully not the other parts. New connections, right? I think the atmospheric escape work has been super exciting, and I think Dave has one of the strongest programs to do this and apply what we've learned in the solar system to exoplanet systems. And then I started thinking about other people I could work with. I thought about Erica Nelson's work with jades and how we could potentially find more unusual brown dwarfs in those extragalactic fields. People like Ben Brown to really connect that fluid dynamical modeling into our 1D models as we think about variability. And then I'm sure the space physics folks here, including Sebastian, can help tackle this brown dwarf aurorae question. Okay, so exoplanet studies are still a growth industry and will continue to be so beyond this 5-year timescale, right? They're getting a larger fraction of both astro and planetary resources in the coming decades. So we'll see our first dedicated exoplanet characterization mission in the late 2020s, Ariel, which will do a statistical survey of exoplanet atmospheres. We'll start to be able to observe a broader swath of exoplanets from ground-based observatories, including the giant telescopes. And then the astrophysics roadmap, right, is really being shaped by this search that I brought up right at the beginning of my talk, right, the search for life in our galaxy. That's driving the mission requirements for the missions that will fly in the 2040s and beyond to be able to characterize temperate Earth-like planets around more sun-like stars. So I'll close it out here and say we're in the midst of a really major advancement with JWST. We've seen really exciting advancements of our studies of both planets more like Jupiter and more like our Earth. And I think CU Boulder would be a really great place to bring this work and to start new collaborations. So thanks very much. I'll take questions.
Thank you, Caroline, for a great talk. I've got time for some questions. Yuta, I'll just kind of toss it underhand to you.
Thank you very much for the interesting talk. Actually, I have two questions. One question is a very quick one. And about, I think you said methane inversion. And aurora can be related. And are there any radio observation for this kind of object?
Yeah.
For auroral emission?
So there are, not to my knowledge, radio observations of this specific object, but I know people are people are proposing for it. But there are radio observations of other objects, and we do see radio emission that's consistent with kind of magnetic activity from other kind of cool brown dwarfs. So we're trying to build up a bigger sample of that, and definitely hoping to go after this specific object directly.
Sounds interesting. And another quick question is about the TRAPPIST-1C modeling. And I think you assume some wind strength and also EUV intensity. And how did you assume?
Yeah, it's a good question. So let me just go back to this. I can show it. There we go. So the three different lines here, which I didn't explain in the interest of time, are three different assumptions about how the stellar spectrum evolves and how what the strength of the stellar wind is. The two codes, the two papers that we use to basically make our parametrized model, use the same code, use the Batts-Raz code to model it. But because they started with different ingredients from the star, they ended up with different results by a factor of 100 in the mass loss rates. So that's the level of uncertainty that we're talking about when we talk about these smallest stars.
So maybe some future stellar observation may help. Yeah, I'm doing stellar observation actually.
Yeah. Yeah, I don't know what the best observations are to probe the stellar wind aspects of it, but I think we should think about that because I think that might really be important for these atmospheres.
Okay. Thank you very much.
Robin Ramstad, co-I on Mach and deputy instrument lead on Maven. A lot of us are thinking about what our studies in the terrestrial planets can tell us about exoplanets.
Yeah.
And so you were leading into that in a few points in your talk, and I was wondering if you have any specific open questions that you think that we can help you with.
Specific open questions. Yeah, I mean, so there's been very little study of how more denser atmospheres are lost from exoplanets, right? That lots of people have studied hydrogen loss, lots of people have studied water loss, right? Because you dissociate and then it's losing hydrogen. There's been much less of like CO2 loss. And so I think to me, that's the biggest uncertainty is how CO2 loss works in different regimes, right? Different timescales for the star, how you can dissociate CO2 in the upper atmosphere, right? And then lose it.